Section 16.2 introduces a new kind of integral called a line integral. Our goals here are to compute line integrals of multivariable functions and interpret them physically. So far in studying calculus, we've integrated functions over the real number line. These are single variable integrals of the form the integral from a to b of f of x dx. We've also integrated functions defined over the plane. This is the double integral of f of xy dA. And we've integrated over three-dimensional domains. This is the integral of f of xyz dv. In this chapter, we will integrate functions over a curve in either 2 or 3 dimensions, though more are possible. For example, here we have a curve in 2-dimensional space. We can define a function, f of xy, and graph it like so. The area that we're interested in integrating over then is the area between the curve and the graph. That means what we're actually interested in is the height of the graph over the curve, and the rest of the graph isn't really going to matter to us. The naive approach to integrating a function f of xy over a curve defined by r of t equals x of ti plus y of tj would be to take the component functions x of t and y of t and plug them in to the function f. We would get an integral like the integral from 0 to b of f of x of t comma of y of t dt. But this would be dependent on our choice of parameterizations. If we replaced t with 2t, the curve would move twice as fast, and we would obtain half the area. A single variable example to motivate this is to see what happens if we have the function f of x and we replace it by the function f of nx, which moves n times as fast. When n equals 1, we obtain the full area under the curve, but as we move faster, the area shrinks because it is no longer as wide. Instead of being dependent on our choice of parameterization, our integral should compute something that is geometrically inherent to the curve. The obvious choice would be to compute the actual area beneath the graph and over the curve. In order to do that, we need to compute the base and the height of this function. The height, of course, is the values of the function. The base should be the actual distance traveled along the curve. How would we compute this geometric area? Well, we could take some test points along the curve and subdivide it, like this. And then, over each little subinterval, we could build a rectangle. If we added up these rectangles, we should have an approximation of the area underneath the curve. The heights of these rectangles are just the value of the function, which we're used to computing when we compute an integral. But how do we compute the bases of these rectangles? Well, we can compute them by taking the change in x of each rectangle and the change in y of each rectangle and using the Pythagorean theorem. We'll have to do a little bit of algebra to turn this into something that we can actually integrate. Here's the algebra of that approximation. The area is approximately equal to the sum of the height of the rectangles, which is just the height of some test point xi star yi star on the curve, times the base of the rectangle, which is the square root of the change in x squared plus the change in y squared. In order to get this into something that we can actually integrate, we'd like to write this as a function of t for our particular parameterization of the curve. What we do with f is straightforward. We replace the xi and the yi with xi of t and yi of t for a particular t. In order to make this into something we can integrate with respect to t, we can factor out a delta t squared from inside the square root. As we take a limit as delta t goes to 0, this, by definition, becomes the integral of the function f of x of t, y of t, times the square root of dx dt squared plus dy dt squared. This is the formula that we will use to integrate with respect to arc length. A more compact way to write this is to write this as f of r of t times the length of r prime of t, because the value that is square rooted here, or the value computed by this square root, is just the length of the tangent vector. It will also sometimes be useful to integrate just with respect to the change in either the variable x or just the variable y. If we do that, then our summation would be f of xi star yi star times delta x. Again, if we want something that we can actually integrate in terms of t, which is the variable of our curve, we can substitute in x of ti and y of ti, and we can divide by delta t and multiply by delta t. Taking a limit as delta t goes to 0, this gives us the integral f of x of t, y of t, but instead of being multiplied by the length of the tangent vector, it's just multiplied by the derivative of the x component function. What is this actually measuring? Well, it's not terribly geometrically relevant. But in this case, instead of thinking about the full length at the bottom of these rectangles, we're thinking only about the x component of that length. If we want to see the x component of that length visually, we could rotate our point of view so that we are looking directly down the y-axis. From this point of view, or in this projection, the rectangles appear to have a base which is just their change in x, because we can't see the change in y at all. And so this integral is actually computing the area under the curve when viewed or projected into the xy plane. We recently learned about another way of integrating where a vector function is involved, and it's important to recognize the difference between these. A plane curve is defined by a vector function, but integrating a function over the curve is not the same as integrating the vector function itself. There's almost no relationship between these two types of integrals. Integrating the vector function itself was best imagined as integrating a velocity function in order to get a total change in position. In this case, r of t represented a displacement or direction of travel. On the other hand, the line integral of f of xy over the curve c is a way of computing the area between the graph of f and the curve c. Like many of the other integrals that we've learned about in calculus, we initially define it geometrically, but there are many applications which are not as geometric in nature. We defined the line integral over c of a function as being the area under a graph, but it can also be useful for integrating any function so long as that function is a rate with respect to distance. Here are a couple examples. One is if we have a price function which tells us how much it costs to build a mile of railroad track at various points x, y, then taking the line integral of that function would give us the total cost to construct a railroad following the curve c. Similarly, if we have a function f which tells us how much fuel is consumed per mile traveled. For instance, f might have higher values on hilly terrain and lower values on flat terrain. Then integrating f over the path C would give us the total fuel consumption to drive along the path C. Let's compute an example. In this case, our curve will be the line segment from 0, 0 to 3, 4. Our function will be the function x squared plus cosine of pi y. And let's compute the line integral of this with respect to arc length. The first thing we're going to need to do is to find a way of expressing this curve in terms of a variable t. This is a line segment, so what we need for a line segment is r of t is equal to some initial point, r naught, plus t times the vector, where t is going to go between 0 and 1. What is this vector? Well, v is the vector that gets us from 0, 0 to 3, 4. So we can just subtract the coordinates, or do it in our head, to get that v is 3, 4. R naught is our starting point, which is 0, 0. And so our r of t is equal to 0, 0 plus t times 3, 4, which is just t times, is just 3t, comma, 4t. Great. Now we have something that we can plug into f. But remember that computing this line integral is going to be taking the integral from 0 to 1, because that's our range of t, plugging in f of r of t, so that's f of x of t, comma, y of t, and multiplying that by the square root of dx dt squared plus dy dt squared. All of this is dt. So let's compute these things. Plugging in x of t and y of t, that's just 3t and 4t, into the function, gives us 3t squared plus cosine of pi times 4t. But this has to be multiplied by this square root. dx dt is the derivative of 3t, which is just 3. So we get 3 squared. dy dt is the derivative of 4t, which is 4 squared. You probably remember that 3 squared plus 4 squared is equal to 5 squared. And so this is going to give us the integral from 0 to 1 of 3t squared plus cosine of 4 pi t times 5 dt. Now we just need to evaluate the integral. The antiderivative of 3t squared is t cubed. The antiderivative of cosine is a simple u substitution. It's sine of 4 pi t over 4 pi. All of this is multiplied by 5 still. It's a constant multiple. It's evaluated at 0 and 1. When we plug in 1, we're going to get 1 cubed plus sine of 4 pi over 4 pi. When we plug in 0, we're going to get 0 cubed minus sine of 0 over 4 pi. These three terms are all 0. The answer is 1. What does our integral represent? Well, it represents the area under the graph of the function x squared plus cosine pi y, but over the line segment from 0, 0 to 3, 4. Actually, the graph of this function is negative at some points, and where it goes below the xy plane, as you might expect, we count that area as negative area. As mentioned in Chapter 13, you're going to be expected to be able to parameterize the following plane curves in order to compute their line integrals. A line segment, like we did in the last example. We also should be able to parameterize a circle of a given radius, and we should also be able to parameterize the graph of an explicit function. Our last example, which motivates our next section, is to consider what integrating the function 1 with respect to arc length computes. Well, remember, integrating with respect to arc length gives us the area underneath the graph. The function f of xy equals 1 is a constant function. Its graph is the plane z equals 1. That means that the area underneath this graph will have a constant height of 1. We can actually view this yellow area here as a rectangle that's just been curved somewhat. And so the integral over c of 1 ds is equal to the area of this rectangle which is just the length of the base times the height. Well, the height, in this case, is always 1. And so what this is computing is the length of the curve C. We're going to take that idea in order to compute the lengths of curves in our next lecture. In the meantime, here are some questions to make sure you understand the way that we set up line integrals.